with geotech engineering and testing, and we're going to be talking about forensic evaluation of structures. We had about 404 people RSVP'd. We have a lot of building code people. We also have a lot of structural engineers, architects, and civil engineers on the audience. Let's see. If you need to reach me, my name is David Eastwood, and my email is de@geotecheng.com. My number is 713-699-4000. I work for a company called Geotech Engineering. By the way, if you have any questions, type in your questions in the Q&A section. I typically answer them as I go through. That way it's relevant to what the slide is. So that way you don't have to wait all the way to the end.
Awesome. Awesome. Great.
I work for Geotech Engineering located in Houston, been in business for 36 years. We do geotechnical, environmental materials, and geoforensics. We got a staff of 60 engineers, geologists, technicians, support staff. We work in Texas, Louisiana, Oklahoma, and New Mexico, and we have our own rigs so we can respond quickly. We're going to be talking about commercial stuff. And so it could be a project, could be a school project, or this is City Houston Command Station out there on Wilcrest in Houston that's got a lot of foundation problems, or it could be a house project. These structures can experience distress and cracking. Those Italians can do, the wine, but I guess the foundation is not their cup of tea. Their structures can settle. Here's some design errors out there that we can cover on our projects. This is a campus of Rice University. If you go in there, you see some of the CMU walls over there are cracking up. And there's a lot of highly expansive soils in Rice University, a lot of trees, brick cracking. Yeah. It's an apartment building out there. It's got distress on it. It's got what we call center lift. The center of the slab is coming up. So it opens up at the top. More brick cracking. Here's basically cracking right there. There were separations here. You see the separation here on a commercial shopping center. This is a strand in Galveston. You see the brick cracking right there. Brick cracking right there. This is a church in Bel Air, Texas. And I had a lot of brick cracking. This is a great beam cracking out there. It's got a hairline crack on it. Sam's Club, go out there.
That's just a hairline.
Oh, yeah, if you represent the defendant, that becomes the hairline. If you
right. Yeah, good point.
Plaintiff, you can put your hand in it.
Right.
That's a floor slab cracking. And Sam's Club was out there shopping the other day. You see the more concrete floor slab cracking here, alligator cracking, sheetrock cracking inside a residential structure. This is a medical facility out there in Stafford, Texas. See the sheetrock cracking in it. Ceiling tile cracking, sheetrock cracking, more cracks. Ceiling tiles out of whack because the walls are moving. This is a City Houston Command Station. The floor slab heaved up. The wall didn't have any place to go. So basically, it just bulged up. You see it's all basically bulging right here. This is a tile in the bathroom in the school project. The floor slabs are moving.
Is that command center wood walls?
No, they're steel studs.
Oh, okay, yeah.
Okay. So this is again part of that medical facility. Doors are not closing, they're not square. Yeah, basically what happened was the walls moved so much it broke the glass here. They don't use the door, so they walk through the window and go to their offices. Here's the wall. That's what we call hovering wall out there. It's just separated from the floor slabs.
I haven't seen that yet.
Yeah. This is a Montessori school out there on Wilcrest. Doors don't close. All the frames all messed up. Highly expansive soils. We got a lot of it in Texas. Conditions, moisture coming through the slabs. You see the wood floor out here is all swelling up here, bulging. You see the tiles moving up here.
Lubbock, Texas amended out the vapor tartar requirements underneath concrete slabs. They didn't feel like it was necessary there.
I don't know. Okay, here's again, you can see the bubbles underneath the floor covering there. Moisture coming in. Now this warehouse here, this portion of the warehouse, they had vapor retarders underneath it, but this area here, they didn't do it. They didn't put anything underneath it, so moisture came through this. I didn't know what to do. I just didn't have an answer for them. Basically, I told them you have the jackhammer to put a moisture barrier there and pour it again. And tiles distress, tile separation. See the tile cracked up over here because of the movement. This is the grate beam corner failure. Basically, this is not a structural problem. Usually it happens because of absence of bond breaker between the brick and the concrete in here. And the way to fix it in here, you go out there and you get a non-shrink grout and some bonding agent and put it back in there. Slope failure. This is a house out there on Buffalo Bayou, the doctor's house I remember out there. The whole backyard fell into Buffalo Bayou. They went out there, put concrete bags in there. It made it heavier, so the whole thing even failed more. So that was a major lawsuit on that one. You see a landslide here, house sliding down on the slope. Buffalo Bayou again, parking lot failure.
Did you see a lot with when Harvey came through? I bet it caused a whole. Was it pronounced in as far as the failures? Did it make a big difference? We had a lot of
Buffalo Bayou failures after Harvey.
Yeah.
Retaining wall failure, and this happened after the flooding of the Harvey. Just broke this wall here, and you can see the San Antonio, the retaining wall here is an MSC wall, mechanically earth stabilized wall, will strips, and this wall basically they didn't check for global stability, and it was not engineered. So 250 houses had to be basically impacted. And people had to move out and they had to go back and fix everything. The builder went out of business. And now the city of San Antonio is requiring engineering drawings on their retaining walls. So this is next to Lake Conroe here. I was out there. They called me and said, hey, we got a bunch of failure in our yards and stuff. Come here, take a look at it. These are expensive homes out there on Lake Conroe. These guys wanted to dig this ditch in here so that they have a channel for the water. They can put their boats in. As they did that, the retaining walls will start failing. And you can see in here, the whole backyard starts cracking. The pools started moving. They were going to connect this channel to this channel. And so as this started moving, the walls starts moving. The backyard started cracking. Flat work started separating. Here's another one in League City, Texas. These guys are next to the bayou here. And you can see the bulkhead is moving. It was not engineered. So as the bulkhead started moving, the whole backyard, these beautiful pools, everything started moving. Cracks starts happening. Everything starts moving. And the backyard, everything's separating. Major litigation. Somebody's got a question. Let's see what we got here. Do we need a sign anywhere? No, we have your names and everything, so we know who is here.
Yeah, I used to live on Lake Granbury. I've seen more than one of those bulkhead walls fail, and you can tell when somebody does it right versus when somebody's cutting corners for sure.
This is a major situation here. We got a lot of money, and in parts of Texas, like in Houston, we have dispersive soils. Dispersive soils are easily erodible when they get wet. These soils contain high percentage of sodium ions. If you go look at some of our channels out there, you see all these voids in here, these tunnels in there, and water just washes out and create these tunnels in here. Surface water does that, rainwater, surface drainage. develops these erosion gullies. And
the high sodium ion, that just makes it more, it makes it wash away easier. What does the high sodium ion do?
Well, because of the chemical reaction between the silica and the sodium ions, it makes it more erodible.
Oh, okay.
Got a question. What types of geotech analysis performed to evaluate soil stability, like shown in the backyards that are shifting, or did the pattern itself prove the case? When you have slopes out there on projects, you got to do soil testing and get the soil samples and test them for various things, including soil strengths and also dispersive soils. And as you do that and you do slope stability computer modeling, then you can check to see if the slope is failure. This is a project out there in Veterans Memorial and Beltway 8, where we have dispersive soils. They had these little tunnels that you couldn't tell from the surface. The cops were chasing somebody out there. The cops fell into one of them, broke his back, major litigation to sue the homeowner association, the civil engineer, the geotechnical. They didn't check for dispersive soils out there. So that was a major issue there. Buffalo Bayou failure. We have a lot of failures along Buffalo Bayou. It's a beautiful golf course out there in Houston. And if you go out there, it's just very expensive to join. They were fixing the channels along Buffalo Bayou. They want to make it green and all that. So they put geotextiles in here. They didn't check for global stability of this thing. So as they did that and grass starts growing, the water went up and went down. They had what's called rapid drawdown. And the whole channel starts failing. And it starts failing, and major litigation against the civil engineer. And you can't play golf past this red line here this way. And these are a bunch of attorneys that are looking at it. So that was a major, I think it was like an $8 million, $10 million deal that was settled on. Let's see, you got a question here. What types of geotech analysis? We already done that. Let's see, we got chats. Please don't interrupt the presenter. Okay, thank you. So anyway, you can see the slide of the failures. That was a major case out there. Bulkhead failures. You know, this is a bulkhead behind in an office building. The whole thing starts moving and bulging here. You're out there on 610 Loop in Houston. You can see the offices. There's a lot of cracks inside on this thing of the offices. This is another bulkhead failure, Colorado River in Matagorda County. The whole anchoring system failed because it was too close to the bulkhead. And it was within what we call active zone. This is another case, a bulkhead case, where these guys come over here and unload. The ship comes in and unloads gravel. They told them, yeah, you can take the load. But as they started unloading the gravel on top of the pier, the whole thing failed. That was another litigation case where the structural engineer and the contractors were sued on this because they couldn't take the load. Building failure. This is China. They had these building on piles out there in China. And what they did was, this is the building. They made an excavation in front of it, put the soils behind it, and he surcharged the soil, and it basically had a failure, cut all the piles, and the building starts dropping. We have a lot of active geological faults in Houston, Beaumont area. If you have projects built on top of these active faults, it starts cracking up. So on a lot of our projects, when we do work, we check for faulting. We have faults in Dallas, San Antonio, Austin, but these faults are not active. Pool, we got a lot of pool movements in Texas. This is a pool that hydrostatic pressure pushed it up. They were cleaning the pool on the weekend, and the hydrostatic just pushed it all up. There was major lawsuits and all that. I'm gonna get into it. Parking lot, what we call punch-through failure of the columns.
Are there maps of those geologic fault areas?
Yeah, it's on our website. If anybody goes to our website, which I had it, and I'm going to show the website again, you can download them. And so this is a project in Dubai. They were excavating for a building out here with the crane in here. They had a leak over here. And they didn't do anything about the leak. They thought it was not a big deal. And the leak got bigger and bigger, and then just the whole thing starts coming in the channel, and you just fill up the excavation. They're still sitting in there underneath it. So crane failure. This is a medical center in Houston. This is the crane in here. They got a 2 yard of concrete, about 7,000 pounds. And they start delivering it. And what happened was the crane, the outrigger failed and punched through the soil. The soil was not compacted, it was sand. The concrete container fell on this guy's leg and chopped it in half. So that was a major case there. You can see the outrigger sinking to the sand in here. And of course, you can see the limestone out there, dissolving out there, creating all kinds of problems out there in Florida. Whitney Lake slope failure out there near Dallas. Anybody other south of Dallas out there, you can see the crack in the rock right there. There's a house there. And you can see the whole thing starts failing. That slope failed. Efflorescence. All pools are designed to protect from neighborhood. I've got a presentation, Hilda, I got a presentation on pools coming up in 2-3 months that addresses a lot of the questions about pools. I'm going to talk about it a little bit in here, but I've got a 2-hour presentation on pools that talks about how to protect it from trees. Basically, trees suck moisture and can cause shrinkage on one side of the pool where the trees are. Also, tree roots can lift some of the pools that are shallow. Efflorescence. And you can see on a lot of projects, you go out there, look at the brick, and you see these white powdery stuff, you know, crystallized on top of the brick. It's a school project out there in Tyler, Texas. And to have efflorescence, basically efflorescence is a white, fine white powdery deposit of water-soluble salts left on the surface of the brick as the water evaporates. And a required condition to have efflorescence, there must be water-soluble salt present somewhere in the wall. There must have sufficient moisture in the wall to render the salts into a soluble solution. There must be a path where the soluble solutions to migrate to the surface and basically crystallize. Sources of efflorescence are alkaline, sodium and sulfates, potassium sulfates. To try to minimize, I mean, I have efflorescence on my brick in my house, and I use all kinds of chemicals. I couldn't get it off. I guess the best thing is to use low alkali cement when you're actually doing the mortar for the brick. Concrete pavement distress. We have a lot of concrete pavement failures around Texas. I always see them in Dallas, flower mounds. And you can see the concrete, it's concrete, there's no steel in it. It just cracks and falls. That's a big parking lot out there near a big hotel out there, Marriott near Galleria. And you can see basically joint failures in here, pumping, more cracks. So these are concrete failures. Here's the soil coming through the cracks in here. You can see dark soils coming, just pumping through the soil. This is Flower Mound, Texas, joint separation. Flower, you got flat work out there in Willcrest, Houston. Parking lot out there near Shepherd in Houston. Asphalted concrete. It's a parking lot out there, parking right next to Houston Airport System. They didn't have much base, they didn't stabilize subgrade. So the whole pavement starts failing. Major litigation there. This is the attorney measuring the depth of the pond, the pothole there. So what is failure? A failure is defined as a foundation, structure, component, or a facility that doesn't perform as intended. A failure does not have to involve collapse or catastrophic events. foundation that exhibits excessive differential movement, parking lot that ponds water, roof that has excessive deflection, masonry wall that cracks because of lack of expansion joints, basement wall that leaks, pools that are moving and cracking. They are important to the building owner and who has to deal with the cracked foundation and the walls, and the contractor has to repair it, and the engineer who gets sued for faulty design, and the attorneys that make all the money. Scientific approach for determining the cause of the failure are: you state the problem, what the problem is, perform observations, formulate hypothesis as a cause of the problem, try to hypothesis by observation, analysis, and physical test, analyze the results, make final conclusions. Develop a damage model. The attorneys always want you to develop a damage model, see how much it's going to cost to fix it. And if you're a plaintiff attorney, he wants you to come up with the most expensive way of doing it. Qualifications of the forensic engineer: got to be an expert in the subject, formal education, experience, licensed engineer, active in technical societies, fair, impartial, and ethical, truthful, objective, avoid conflict of interest. Must be a detective, kind of be someone who likes to discover information about crimes and find out who's responsible for them. You have to be able to think outside the box. You have to enjoy digging for the truth. Got to be a good presenter, can communicator, be able to handle deposition and trial work. So we have basically a major, this is a kind of a format that when we talk about failure, what causes it as it relates to foundations and structures and pavements and slopes. We look at design, inadequate geotechnical report, inadequate structural design. We look at construction to see if there are faulty construction. They didn't follow plans and specifications. They use the wrong materials. Concrete, instead of being 3,000 PSI, it's only 2,000 PSI. Maintenance, we look at the trees, drainage, slopes, and wear and tear. Could be like sewer leak or plumbing leak. Okay, inadequate geotechnical report. Inadequate site condition description is very important in geotechnical reports to have pictures of the site and describe if there's a fault there or if there's a slope there. You got to show that in the geotechnical report. Incorrect bearing capacity. In parts of Texas, we got perch water table. You need to evaluate that. That affects the bearing capacity. You develop a perch water table when you have sand over clay and it rains and ponds water on top of the clay and the sands become saturated. Pier, a lot of foundations in Texas where you have expansive soils, they have shallow footing depths. So these piers are too shallow, and the geotechnical reports do not consider the effect of expansive soils and trees when they come up with the footing depth. Incorrectly estimated movement values on Y sub M and E sub M on PTI, Post-Tensioning Institute. Inadequate foundation recommendations regarding perch water table. Inadequate structural design, did not discuss the foundations and risk with the client. When you do a structural design on a structure, you got to discuss the risk of different types of foundations with your client. Certain types of foundations are riskier than the others. Use a structural slab with piers. That's the least basically distressful foundation system. Use a slab on grade with no piers, just like a post-tensional slab or a conventional reinforced slab. Although many of them perform just fine, they have higher risk of foundation movement as it compares to a structural slab system. Foundation design without a soil report, that's a big no-no. You can lose your license as a professional engineer if you go out there and design a foundation without a soil report. I've seen a lot of failures because of that. Misapplications of the design to site conditions, slope sites on active faults, using wrong type of foundation for the soils. Engineer of the record should have adequate information, including drainage, slope, existing trees, future trees and vegetation prior to foundation design. That's really important thing here. As the engineer of record, who's the structural engineer in this case, must have a lot of information. A lot of the structural guys don't go look at the site. At least they got to do a Google site visit. And also the Geotech should have the pictures of the site in their report. inadequate construction. We got plans on the spec, and to see, we're going to check to see if the contractor built the building in accordance to plans on spec. So we checking to see in here if this building had piers on it or not. So you dig out there next to the foundation where there's supposed to be piers to see if there are piers. Are there grade beams there? How big are the grade beams? You measure the grade beam depth. Also, you measure the grade beam width to see what the width of that grade beam is. If the beam is supposed to be 12 inches, it's only 8 inches. Basically, the stiffness of that structure is really is much weaker. So you got to check all that. The beam depth and width, it's very important. You check to see if there are piers there. If the piers are there, then you got to check in to see if this is the pier, this is the bell, what size bell you have. You can measure the distance from the pier to the pier tip, bell tip, and you can estimate what the bell size should be. So if this distance is 12 inches, for example, and this is a 12-inch piers, that bell is 36 inches. Again, this is the pier. This is the tip of the bell. You measure in here, in this case, is 7 inches. So if this is 12 inches, so that would be 14 plus, that's a 26-inch diameter bell. And if the design was 36-inch bell, well, it's a faulty construction. This is a pier that was too shallow. Again, that was a design flaw. They put the pier too shallow, and so there's a void underneath the pier, and the soil, the expansive soil is grabbing the pier and pushing it up. Here's the void underneath the pier. If you go look at a house or a building and your piers and grade beams are well connected, and this is heaving over here, that means the piers were too shallow. Yeah, if it's good connected and heaving, it's too shallow. Now, if there's a separation between the pier and the grade beam, and this is heaving here, that means the piers are deep enough, then basically the grade beams are lifting up the slab off the ground because of the expansive soils. These are some sound walls out there in the city of Pearland, Texas. And if you go out there and look at them, you see the piers are kind of lifting off the ground. These are shallow piers, the highly expansive soils out there. And these are heavy loads on this thing, but expansive soils are grabbing these piers and pushing them up. Columns, you go inside the buildings, on parking garages and commercial projects. You got to have the joint needed near the columns in here because the floor slabs may be moving separate differently than the columns. Columns are heavy, they don't move. The floor slabs move up and down, so you need to have a joint, otherwise you're going to get cracks around your columns. So we recommend to have joints around your columns here so that you don't go through all this cracking and replacing. Here's a Kroger store out there in New Caney, Texas. These are the columns, and they have fabric in here as a joint between the concrete floor slab and the columns. There's a lot of times you have your anchor bolts like that. That's how you put the columns in. You've got a joint out there. It's a diamond shape or circular shape. Columns out there, joints there. That's a column as a finished product for that Kroger store. Instrumentation. If you want to know how much movement you're going to have, you put crack monitors out there on your brick or your sheetrock. You can monitor movements of the sheetrock or brick as a function of time. Here's the sheetrock here with a crack monitor. This is a two-dimensional. It goes up or down or sideways. Now, if you want to know three-dimensional movements, these are crack monitors that are three-dimensional that you can put on the concrete or sheetrock and measure the movements in 3 dimensions. Non-destructive testing, if you want to have evaluated to see if there is movement, if there are steel in your slab or your slab concrete thickness, you can use ferroscan. In this case, we're trying to find out where the steel is and what size of steel are they using these warehouse floor slabs. You run it on the floor slabs in here at 10 foot by 10 foot area. And here you can tell where the steel is, what spacing it is, and what size of steel you have. You can do that with GPR as well. In this case, you have number 5 bars, 8.5 to 10.5 foot, 10-inch spacing. The specs called, detected spacing is 10.5 inch in X direction, 8.5 inch in Y direction, and it's number 5 bar. This is a warehouse building. They want to know where the steel is and the floor slab thicknesses are. So in this case, what we do is we use GPR and we find out the steel spacing is 12 inches, 14 inches. The specs call for spacing of about 10 inches. So this is a little bigger than that, 12.5, 13 inches. And it says minimum concrete cover over the steel should be 2 inches. Here we measure 3.2, 3.1, 3.3. So the steel is a little lower than where it's supposed to be. Sometimes we find steel all the way in the bottom of the slab. That's the case when they don't use chairs or they use rolled wire mesh. We use sound velocity in concrete to figure out concrete thickness. The sonic device, this thing hits the concrete, sends a velocity wave, sound wave through the concrete. The sound travels through concrete at about 10,000 to 14,000 feet per second. Sometimes slower than that if the concrete is weak. And in this case, we go in there. This is the floor slabs. We core it at these locations and calibrate the equipment with the core thickness. Once we calibrate it, we go in there and develop a grid of the floor slabs. And from that, we find out what the floor slab thicknesses are. In this case, concrete's supposed to be 6 inches. And you see a lot of 5-inch here, 5.38, 5.19, 4.79. You can see a lot of the concrete is lower than what it is. Somebody's asking a question. Somebody asking, have you ever seen a crack monitors that are electronic? I have not seen one, but I'm sure there is out there maybe, but I've never seen one. Typical tolerance for slab thickness ACI 117 is plus 38 and minus 1/4. So your slab should not usually be more than 3/8 of an inch in thickness, greater than your design, and less than 1/4 of an inch in thickness. Here's using the, again, using the sound velocity going through the concrete. We calibrate the machine in the parking lot. They want to know what the parking lot concrete thickness is. We calibrate it. We go over here. Parking lot here is supposed to be 8 inches. We measure in the parking lot 7.8, 7.93. Here it's supposed to be 6 inches. We measure 5.8, 5.78, 5.84. Pretty close. So you can use sound velocity and determine thickness of the concrete. We'll also do geotechnical borings. We do the borings for the projects next to trees. Trees tell us a lot about foundation systems. The roots from trees extend to the areas where there's oxygen and water. And that defines your active zone depth. So it's very important to know what your active zone depth is from the trees. You do the borings. Like I said, you do the borings next to trees. You get these root fibers that defines the active zone. We core inside the building. If the core drops, there may be a void underneath the floor slabs. And then we check that void to see if the pad has settled away from the slab, or there's poor compaction. Here's a crack in the floor slab areas. When you put a camera underneath where you cored, you see the crack right there in the floor slabs, and you see the pad is separated from the floor slabs. So you got a giant, basically gap between the floor slabs and the pad. That usually happens on the older buildings. And you can see the grade beams go over here. The vapor barrier is gone, basically deteriorated. It's the vapor barrier right there. So we core, we get soil samples. Here's the crack in the concrete. We start doing with the rig. It's a portable rig. You get soil samples. It's an AutoZone. That's what the soil sample looks like when we get it. This is a house in Seabrook, Texas. It's a crawl space house. They didn't have his own soil report when they designed it, put the piers at 8 feet. highly expansive soils. We got the soil samples underneath it. And that's what the soil looks like. Highly expansive soils, beautiful clay. Soil sample. We also run elevation using zip level on the foundation to see what kind of elevations you have. And this is a zip level. You put it out there, and it gives you relative elevations of the foundation. You have a reference point, and you go around the whole commercial or residential building, and this is the zero. And you measure the relative elevations of it. It's minus 0.3 here. So you get the elevations. You can also do like Texas A&M is doing, put cables in your foundation. These are elevation cable called steadfast. You put these cables in there in your grade beams. Before you pour, you put these blue cables in it, and then you connect it to a device, and it tells you if the cables are moving, and that gives you your floor slab elevation movements as a function of time. You pour the concrete, and you can measure basically elevations in X, Y, Z. You can get them at 10-foot spacing throughout the project. Measures can be manually or monthly or weekly. You can monitor it. You get contours of the elevations at everywhere. Each month, as desired, analyze high resolution compared to historical summary statistics. Reading sets of highly reputable, repeatable, and believed to be best in the industry. So this thing gives you elevations. You can get it weekly, daily, monthly. This is a house out there sitting on expansive soils. The house starts moving. These are the elevations. This side of the house is minus 0.24 inches. Here is minus 0.2. Is it heaving or is it settling? Well, this is a new house on expansive soils. So typically 95% of the cases where you have new construction on expansive soils, there's a heave. So it's heaving on this side of the house. There's about 2.2 inch differential movement across the slab. This is another building that's moving. You got one side of the building, the elevation is 3.75. The other side is 3.75. It's a medical facility out there. And you can see in here, there's a minus 1.8 plus 1.4. So roughly about 3.2 inches of movement in the floor slab areas. The whole inside sheetrocks are all cracked up. This building was designed without a soil report. And so the whole thing is moving. It was a big pot, a lot of water underneath this building. This is a building out there on Richmond Avenue in Houston. It's a tilt wall building. If you go out there and look at this building here, when it was built, it was a heavily wooded site, highly expansive soils. And the tilt wall panels are popping out one after the other. The piers were too shallow. They didn't put enough fill underneath the floor slabs. So all the panels are moving. You look at the elevations, elevation plus 3/8, elevation minus 7/8. So there's a whole bunch of slope out in here. There's a three-dimensional of the slab movement. This is HISD, Houston Independent School District. And if you look at it here, is elevation minus 0.38, and you got elevations here of minus 0.5, almost 5 inches of differential movement in the floor slab. This is in Pearland, highly expansive soils, was poorly designed. So here are some concepts for those of you guys who are structural engineers. There's a thing called tilt. Tilt is planar rotation measured over a length or width of the foundation. That's X over Y. That's tilt. I mean, Y over X. Y over X. That's the tilt. You can have up to about 1% tilt and 1% slope. Slope is a differential elevation between 2 points divided by the horizontal distance. And so that's a really important thing to remember. Somebody's asked a question. All right, I guess it's not a question. Here's a house, you get the elevations on it. And you see the plot the elevations, you see all parallel line. That means that slab is tilting. If something tilts and it's usually less than 1%, you don't see cracks. The whole thing is moving as a unit. There's another concept called deformation, which is changing shape of the foundation after the original foundation construction. Deflection is a maximum deviation from a straight line between 2 points. Straight line, not horizontal line. Deflection ratio is the deflection divided by horizontal distance over which it occurs. So this is the correct elevation. This is basically deflection between points 1 and 3. At point 2 here, that's a straight line. That's the elevation delta. This is not delta. It's not deflection. This is the deflection. There's a guideline by Post-Tensioning Institute on Guide for Performance Evaluation of Slab on Grade Foundations. Also, another organization that I'm a member of, and I am president, used to be, and founder, called Foundation Performance Association, has a similar document to look at elevations, and from that, determine if your slab has failed or it's not failed. L over 60 is the number what we're looking at, basically 1 inch in 30 feet. So this is a house. That's a house in Austin. If you look at the elevations in here, section BB, if you look at the elevation here, get a cross section of it and run the numbers in here. This thing, the slab is moving this. The deflection is L over 563, which is less than L over 360, which is 1 inch in 30 feet. So it passes. The tilt is 0.3038%, less than 1%, it passes. Now, if you go to get a section AA on the second floor, you run the numbers, and that's what the slab deflection is. The deflection is L over 318, which is greater than L over 360. So it fails. The slope is 0.13%, which is less than 1%, so it passes. TRCC, Texas Residential Construction Commission performance standards are: your floor slab crack should be less than 1/8 of an inch. Your flat work should be less than 1/4 of an inch. Flat work separation in expansion joints 1 inch. Stairs should have less than 1/3 of an inch settlement. Carports and garages separations 3/16. Sheetrock crack should be less than 1/32. Masonry, the brick and masonry separations and cracks less than 1/8 of an inch. And let's see, try to read this. Joint gaps in brick should be less than 1/4 of an inch. Some measures to reduce heave on foundation is use a sprinkler system all around the building. Put space between the driveway and exterior grade beam. You know, if you have a situation here, you got grass here and concrete here, this area gets wet, this area stays dry, so you're going to see cracks in here because this area wants to move up and down. This area does not want to move. Do not use sand. Have a positive drainage around the structure. Do not use sand for grading of the foundations. You can remove the expansive soils depending on your PVR. If you got a site with PI of 60 and active zone of 10 feet, you're going to have to remove almost, 84 inches of soil, 7 foot of soil to get your PVR less than 1 inch. So to get the movement less than what you need to have to be, you're going to have to put 7 foot. We talked about this one. Here's again, you can see the bank building. Concrete here is the grass in here. This area moves up and down. This crack happens right there if you have expansive soils. If you don't have expansive soils, nothing's going to happen. Blockbuster video, and you can see grass over here all around. So it's got uniform moisture. So if it moves uniformly. You want to have your driveway have a separation between the driveway and the house. and the commercial buildings so that moisture around the structure is uniform. If you have a situation, the driveway right next to the wall, this area doesn't move, but this area here where there's grass and plants, there's water, this area is going to move. So you get differential movements and cracking. This is a commercial building. It's got concrete all around it. So what happens is after initial movement that happens because of the tree removal, this thing stabilizes and does not move anymore, but initially it's going to move if the site had trees on it. Benchmark construction. Most of the movements that we get on projects are relative. These are relative elevations, the macro elevations that we get. If you want to get actual elevations, you need to set up a benchmark that does not move and get elevations relative to that benchmark. So in here, you drill a hole in the ground about 20 feet in Houston, 30 feet in San Antonio, and Dallas, and Austin. These are 12-inch holes. You put a helical pile in there, about 20 foot deep. The stem comes out of it like this. You put a PVC pipe around the stem and then fill the area between the PVC pipe and soil with concrete. You fill it with concrete. This becomes, that means the stem can move up and cannot move up and down because it's anchored down 20 feet. Below 20 feet in Houston does not move. So, and in Dallas and San Antonio, I would say go down 30 feet. In Las Colinas, go 40 feet. So you go out there and put this in there, it does not move. So you can go out there and get relative elevations, compare that point that doesn't move on your building. And you get cross sections of the movement, and you can see all the movement of the building, different seasons, different time. You can do it, you know, in November and August, March, and you can see how it's moving. Perch water table. Somebody is asking, can we get a PDF of this presentation? You can get a link on this presentation so you can watch it. You cannot get the slides, but you can get the video of this thing. Perch water table. On a lot of commercial and residential projects where you have sandy soils over clay, the contractor builds a pad with sand over clay. You get a perch water condition. This is a pumping of the soil. Basically what happens is water sits on top of the clay, cannot go anywhere, so it starts pumping.
That's so crazy looking.
Got a question here. What's your opinion on having sandbags in the bottom of the foundation? I don't like sandbags personally. I know in Austin, on the slopes and all those places, they put sandbags out there underneath their slabs. If the slabs are designed structurally that they can span out, you know, the sandbags, it should be okay. But on generally, foundation has to basically reside on top of the compacted soil. So sandbags are not considered compacted soil. So I know builders do it in Austin all the time, parts of San Antonio. And if the slab is not properly designed, it's not good. You got another question here. Again, the question was, can you get a PDF of the presentation? You said, yeah, we say yes. We cannot give the slides of the presentation. We can give you the presentation PDF. The slides we cannot give you. This is a slab out there in the Woodlands, Texas, where you have perch water table. You start digging the beams, it gets filled out with water. The sands just bleed water because it's all saturated. Again, you can see digging next to the building, commercial, and it's a tilt wall building. You can see water next to your piers. You dig next to the grade beam on the residential project, and the water starts coming in. It's all perch water type conditions. Piezometers. Piezometers are basically devices that measures the water level underneath the floor slabs. So you drill a hole in the floor slabs out there. You put the PVC pipe, usually it's about 2 inches in diameter. It's got perforated sections so that the water can flow through it. You put it in the hole, you put sand around it so that the water can flow. And then you can go back and measure the water level underneath the floor slabs. This is the PVC pipe. You measure the water at 7 foot here, 10 foot here. This is about 133 inches here. This is the piezometers that you leave it in the floor slab area to see where the water is underneath the building. You can measure it outside the building too, where the water is. This is a piezometer. It's basically, you got a screen here, PVC pipe with a screen. You put sand around it. Then you seal it with bentonite and grout. This is above the ground section of it. So lift-off testing on post-tension slabs. Sometimes those cables are dead. So you want to know, do a lift-off testing to verify that the design force in the tendons has been achieved. On occasion, a situation require a lift-off to be performed. This could be done. This could be due to elongation be out of bad tolerance or the slab not performing. In addition, some specifications may require verification of the force in the tendon. So to check the elongations on a slab, you get there and get that cable exposed. You connect it to that this device in here. Start pulling it with the jack. You got a calibrated jack here. And you measure the elongation. See how much load it carries. Usually you want to have 26.5 kips of load in your tendon to be able to hold. So typically you do on a typical residential 3 tendons on each side of the slab. Brick, you don't want to have a building that has got brick cracks on it like this. Not acceptable. This whole building here has got only one joint in here, one brick joint. See, like that. See the cracks, there's no brick joints on these walls here, so you're gonna have a bunch of cracks. There gotta be a brick joint here. There's a brick joint here. There's a brick joint here. Brick joint spacing should be at 20-foot spacing. Why do we need the expansion joints in brick? Because brick joints, materials, bricks, and all building materials expand and contract with changes in more temperature, humidity, and other environmental conditions. Because those materials move at different rates because nature will put them in if you forget. Where do we need expansion joints in brick? Periodically in long walls at 20-foot spacing, at offset walls, where short runs of the masonry meet long runs, outside corners where different materials meet, and at junctions with different functions or different heights. Materials. Okay, as part of the failure evaluation, we're going to look at the materials to see if the concrete that was used, was it a good concrete or bad concrete? We check for concrete strength, fill properties to see if the soil that was used under the slab was any good. Was it select fill or was it bank sand? Check the steel, was it grade 40 steel or grade 60 steel? Record the concrete We measure the thickness. This is a moisture barrier underneath it, the slab. Check for where the steel is. You put a machine and break it. If the concrete's supposed to be 3,000 PSI, and if it breaks at 2,000, that concrete fails. ACI 318 says concrete in an area represented by core test shall be considered structurally adequate if the average of 3 cores is equal to at least 85% F prime C and no single core is less than 75% F prime C. So if your concrete is supposed to be 3,000 PSI, none of the value of the 3 cores should be less than 2250. Average of 3 cores should be at least 2550, otherwise your concrete fails. Now, if the concrete strength passes, you do petrographic analysis because you still got those cracks in the concrete. So why do we have concrete? It's got cracks in it, even if you got proper strength. You get the slide cores, you get a slice of it, if these cores in here, and you take a slice of it like this, you put it on the microscope, you inject it with blue dye, look at it. You check for air voids. If there's no air voids, that means it's supposed to have air in it. That means that air is not uniformly in the concrete. Check for water cement ratio. A typical concrete has got a water ratio, a cement ratio of about 0.4 or 0.5. Here's 0.55 to 0.6. That means your concrete is wet, too much water. You look at calcium oxide here, calcium hydroxides in here. These are cured and non-cured cement, the white stuff. These are calcium hydroxide. And you can see the cracks in the concrete. Here's a big deal. You see all these black marks on the aggregate? These are clay soils. That means your aggregates were dirty. So whenever you have dirty aggregates, you have high water cement ratio and low strength. So you check all that. You can also check for air in your concrete. You check for chemical attacks in your concrete. You check for Alkali-Silica reaction. This is the aggregate in here. You get this gel around it and expand and pop outs. Alkali-Silica reaction is between certain aggregate types with cement that forms a gel that causes excessive expansion, cracking, and pop-outs of the concrete. We'll also look at the maintenance, so drainage around the buildings. The drainage, you want to have positive drainage around the building. Positive drainage. You don't want to have this condition where all the water comes next to you. Here's water comes out there on the side of the building. You want to get that water away. You don't want to have water next to your building. This is not acceptable. This is not acceptable. This is not acceptable. This is not acceptable. A lot of times out there on Gessner Avenue out there in Houston, if you go out there and look at it, the landscape architect makes a big mound in here and you got negative drainage towards the building. That's not good. That's the buildings have problems. That negative drainage is not any good. You can see the negative drainage next to this building here. Negative drainage. It's negative drainage next to these apartment buildings. Here's a medical building in Stafford. They put gravel in the planter area. Gravel is permeable, so water just sits next to foundation or the expansive soils. So we don't recommend using gravel in the planter areas. You want to have a positive drainage from your building. Positive drainage. Positive drainage. Positive drainage. Bed liners. They go out there and put bed liners next to these buildings and they build up the area with this the topsoil, permeable. Water sits in here and feeds the expansive soils. Bed liners here. You see the bed liners here. These are brick bed liners here with gravel. This is a house in Pearland. Had all kinds of foundation problems. This is a building out there in Brazoria County. You got a bunch of topsoil in here, gravel, planter area, highly expansive soils, causing building foundation problems here. This guy's a fish pond next to his house. Not acceptable, highly expansive soils and moisture in Pearland. AC units, some of these AC units, they have condensation. And these condensation causing the expansive soils to heave up and down. So this side of the building is moving up. Here's the AC units, the condensation water coming down, and the area gets all wet. So if this was grass, and this side of the building can move up and down due to expansive soils. Gutters, this is not acceptable. You need to have extension pipe and a splash box in here or go underground for your drainage system. Not acceptable. This is an HIST school that's got gutters like that, got a low area, water sits in here, highly expansive soils, poor maintenance, bad gutters here. You want to have the gutters coming to an underground drainage system, get that water from the roof, take it down, and take it away from the structure. You need to have an underground drainage system. Here's a gutter from a building coming out, dump it on the concrete, which is okay. Although water gets in there through the joints in the pavers. Here's, you got a big splash box, get the water away. Here you got water coming next to the foundation, and you have water here and no water here. So this side of the building can move up and down. Okay, somebody is asking a question, is there a situation where chemical drying is applied? No, I don't know a case where you have chemical drying. Again, the gutters are coming over here and dumping in the concrete, which is fine. You can dump the water on the concrete and have a manhole and then kind of some kind of an inlet and get that water away. Here's the gutters going to an underground drainage system. Here's the coming here, going to a flexible pipe in here, coming up, draining at the curb. This building had foundation problem near the Houston airport system. And they look at the roof, it was a slope roof. It drains to one side and they had gutters there. And this side of the building was always wet. And this side of the building heaved up, causing foundation problem. So you should not have the gutters. If they're coming to one side, it's fine. Take it to an underground drainage system. This is a house that had no gutters, good drainage around it, but they had bed liners next to it. So when it rained, water just sat right next to the foundation. It had a perch water table condition. So you go inside the building, water was underneath the slabs. Here's again a house with no gutters, and you can see the depression out there next to the foundation. Basically, because the water rainfall hits the ground, they had a low area. The water would sit next to the foundation. Here's somebody dug next to the foundation. In here, you got a low area, water sits there, can cause foundation problem. That happens when you have a doggy that's hot. So you can go out there and kind of try to cool off. Here's another one. The doggy dug a hole here to cool off. In the areas where you have gravel out there in the backyard, you got the gutter coming in here, dump the water in here, and make sure you got good drainage, some area drainage in here to get that water away. If you have no area drains in the area, or if you don't take that water down to the underground drainage system, this whole area can stay wet and cause foundation movement. So you want to have area drains in this area. Gutters overflow. If you basically, if you have a situation, the gutters are overflowing in here, that means the gutters are not properly designed. Now, of course, it's hard to do that anyway, but this part of the building is going to heave up because it stays wet in this area. Olive Garden restaurant in Conroe. Here's the deal. This building is designed with rock and mortar. If you look at it in here, it's very stiff structure. And then you got planter areas with gravel and bed liners. I mean, it holds the water next to foundation. So I went out there and took some pictures of this thing here. The manager asked me, why are you taking pictures? I said, I'm taking initial pictures of the building so that if it moves, we have some initial pictures, because this is a very rigid, any kind of movement would crack these walls. Here's the gutter coming in from the building, dumping over here, going to an underground drainage system. Area drains. You can see the area drains. Put them as many as you can. You go next to the buildings, these commercial buildings, you see all these little gravel bed area. This holds the water next to the foundation, cause movement. Put the trees as far as you can from the building. These gravel areas with bed liners hold the water next to the foundation. Sometimes you put skirts on the buildings. These skirts keep the moisture from going underneath the buildings. So that's good. Sprinkler systems, if you put sprinkler systems, put them all around the building uniformly to keep all area wet. If you got a situation, you got a sprinkler system here and none over here, this area wants to move up and down, this area doesn't move. Check the planter areas for topsoil. Do not use topsoil where you got expansive soils or sandy soils. In this case, where you have expansive soils, you go out there and put topsoil out there. What happens is this topsoil is permeable. You dig it next to the foundation system and you develop perch water table condition. This will feed the expansive soils underneath the foundation. Grading, you got to make sure you got positive grading away from your building with clays, not sand. You do the grading with clays, positive drainage around your buildings. Do not use pea gravel. This is a building in Bel Air, Texas. The back patio, the back of the house was heaving up. Remove the patio, you see a bunch of sand underneath the building, underneath the patio, holding the water next to the foundation. Bel Air has got highly expansive soils. Structures in slopes. We have a lot of structures in slopes in Houston area. And some of these foundations have shallow piers. They're not engineered properly for slopes. So the whole thing starts failing. See, these columns are not properly engineered. These columns starts tilting. The slope starts moving. Start getting shear moment cracks here. Again, some of these columns are not very sturdy on slopes. And the building starts moving. This is out there in Tomball, Texas. The whole backyard failed. So if y'all building buildings on slopes, got to make sure they're deep enough outside the failure zone. This is a failure out there in South America. This is a house out there in Arlington Court, out there next to Memorial Park. Notice there's space between the buildings, maybe 2 or 3 feet. So you cannot get any equipment back there. The back patio was separating from the main house. There was a bulkhead here. The retaining wall was not engineered to put the timber piles in here and some lagging in here. They went out to put concrete bags in here. This thing starts moving more because it was heavy now. All these columns starts tilting. The patio gets separated from the house. So since there was no way we could get equipment back there, we just told them sell it as is and get out. There was no way we could get equipment back there. This is a doctor house in Memorial. The back of the house was terraced, Buffalo Bayou. The slope starts moving and the whole slab starts cracking. So they had to tear down the whole house. Major lawsuit, the Geotech got sued, the structural engineer got sued. You got to check for global stability when you build a structure on a slope. If you have a house on a slope or a building on a slope, check, make sure the slip circle, if it goes underneath, it's got the proper factor of safety. These are the foundations. Swimming pools, they come in all kinds of shapes. And natatoriums, large swimming pools. World's largest swimming pool in Chile, $1 billion. It's a big swimming pool there. They come in all kinds of shapes and forms. And you can see in here that in this swimming pool in here, water is moving up over here and it's going down in here. So what is that? He said this is a pool out in here in Friendswood. See, this is one side of the pool. This is the other side of the pool. The pool is moving. Guess which side of the pool usually moves up? If you have expansive soils, usually the shallow end of the pool starts moving up. This is a pool out there in Memorial next to Buffalo Bayou here. And it was a vanishing edge pool. There's a big drop right next to the pool. They didn't account for that. So the whole edge of the pool fell into the slope. Major litigation there. This is a pool out there in West University. They wanted to clean up the pool over the weekend to empty the water. And it rained over the weekend and the hydrostatic pressure pushed it all the way up, about 15, 16 inches out of the ground. They sued and the insurance company didn't pay them, said it was safe, sanitary, and livable. So he still can jump off this thing, I guess. They didn't pay him. Here's another one in cypress wood. Hydrostatic pressure is pushing it out of the ground. When you empty the pool, you got to be very careful to go in there and poke a hole in the bottom of it to release the hydrostatic pressure. Otherwise, the hydrostatic pressure can push it all the way up. Here's a pool out there in Tanglewood in Houston, highly expansive soils. Make sure you compact the soils properly underneath the pools. You put steel in it. You shoot gunite. This is when your soils are non-expansive. There's a whole procedure for pool design that I'm going to go over in a couple of months. Actually, I got a seminar on pools in 2 weeks for Greater Houston Builders Association. Anybody wants to go. If y'all want to know about some of these things, send me your email information so that I can put you on our database so that you know about all the seminars that we do. Make sure you got my contact information. Send me this stuff. Here's a gunite, which is a combination of cement and aggregate less than 0.75 inch, which just shoot it dry and add water to it at the valve. Here's where we add water to it right there. So here's where we add the water right there. The way you do pools on expansive soils is you remove the expansive soils and replace it with non-expansive soils, or you do a structural pool on piers with helical piles on void boxes, or use chemical injection. Again, we got questions. Do your questions on question and answer, not on chat if you would. Okay, let's see what it says. See here. I guess I have questions. I don't know.
They were just wanting to be added to your email distribution list.
Oh, okay. Just send me a separate email. Separate email. Pool design approach. We talked about that. Effect your trees on foundations. Trees affect foundations in 3 ways, essentially. You have all these root systems out there. These roots go underneath the buildings, suck moisture and cause problems. Here's how the tree fell on top of this house right there. Here's another one, hurricane tree. Here's another one failing. Tree root systems grow 3 dimensions. And this is my house. I've got a tree going through it like that. This is my vacation house. This is my condo in Florida. This is my backyard. And here's a tree hugger. People like to have trees around their houses and their buildings. These trees cause a lot of problems. Essentially, when you're going to build a new structure, you got to take out all these roots out of the ground. If you build a slab with roots underneath it, with time, these roots decay and you go out and cut slice out of your concrete. This is what you find underneath your slabs. That's where the roots used to be. And water travels there and causes movement. So all the roots greater than 1/2 inch needs to come out of your slab areas. Roots affect foundations 3-way. The first one is root heave. Root systems go underneath the buildings. It starts lifting up the walls, the slabs. You can see the sidewalks. They go underneath trying to get moisture. And as the roots go out there and start distressing the sidewalks and the building, it's a willow tree next to this house here. You go out and dig right next to it, you see the 2-inch root system going underneath the slab. The slab had heaved up inside 2 inches. This is a pine tree next to this house in here in the Woodlands area. And you go out and jackhammer the bedroom out there. The slab was heaved up. You pull out the root system underneath the bedroom. So if you go out and jackhammer the floor slabs, you see all the root systems underneath the floor slabs that go out there and try to get moisture. It's got the hairline roots there. You can see all over the place. So root systems go underneath the slab trying to get moisture. And as they do that, they lift up the slab. You got to get these roots out and cut them out. Go in there and compact that soil, put a vapor barrier and pour concrete again. Soil heave due to tree removal. What happens is you got a building out there. You're going to cut all the trees before you build the building. This is a tit wall building in here. The whole, basically tit wall panels were out of whack. The side was heavily wooded. They cut all the trees. And as you take all the trees, the soil wants to rehydrate. As it rehydrates, it starts expansive soils. This is where the tree was taken out. You can see the floor slab is heaved up. If point H, where you take a tree out, this is expansive soils, and you've got point F away from the tree. Point H near the tree, F away from the tree. Point H heaved up about 6.3 inches. Most of it during the first 5 years. But it can go up to about 32 years of heaving. The soil rehydrates in expansive soils. Point F only moved 1 inch. They rehydrated. So if you got a tree like that next to a building, this tree has got long branches. This is a tree, an active zone of 10 feet. It affects twice the height of the tree. So that's the cone of moisture removal. This whole area is dry. So you build a structure on top of it, you got to have to design for effective tree removal. This is the cone of moisture removal. This is where the tree is. It's a tree root system. This is depth in below ground. This is the moisture removal cone. This is 2H, twice the height of the tree, the depth of 3 feet, still sucking moisture out. So this whole area is dry. You put a tree out there, the soil rehydrates, causes heave. The root spread is bigger than the drip line of the tree. This is in Austin. There were 3 trees in the backyard. These trees moved, and within 2 weeks, the area heaved about 8.2 inches. This is a soil with PI of 50 and 60. Texas A&M did a bunch of research on tree removal. When you take a tree out of the ground where you got expansive soils, the soil rehydrates about 44% the first year. The 5th year, it gets 100% if you got a lot of water available. If you don't have a lot of water available, it can rehydrate for 20 years, 30 years. If this tree dies or removed, next building, if this building was not designed for it, this whole area here is going to move. Trees don't know anything about fences and property line. If this tree dies, this structure here is going to move. If these trees die, this house can move if it was not properly designed. Soil shrinkage to tree moisture removal. These post oak trees out here next to this commercial building here downtown Houston. This is Holcomb, highly expansive soils. You got these trees there. Houston Community College building in here. This building is sloping towards the trees. There's a crack in the floor slabs. There's a crack. And that these trees are sucking the moisture. So side of this building is dropping. University of Texas at Arlington did a research and said, if you got a building here, distance D away tree from a final tree height of H, a D over H of 1, you can have as much as 2.4 inches of shrinkage up here because the trees suck in the moisture. So it's very important to put the trees away from the buildings. If you put it closer, then you need to use root barriers or things like that. This is city of Pasadena. They got all these trees right next to the building. And the edge of this building is shrinking. And, you know, they suck the moisture from underneath the pad, and that pad separates from the floor slabs. So you develop a void underneath the floor slab and the pad. Here's a basically risk of different damage with variety of tree species. Oak tree, you want to put it 1H away from a building. Poplar tree, 1H. Lime, 0.5H. Willow tree, 1H. Elm tree, 0.5H. So this is what we call trees from hell. These trees cause a lot of problems for buildings. Some measures to prevent tree distress. You put the trees as far away from a building as possible. Minimum of 20 feet, or maybe more. Create depressions near the building so that the water comes over here and they have to go underneath the building to get moisture. Put sprinkler systems next to trees so that the root barrier roots should not go far away. Put in root barrier systems so the roots grow downward, not laterally. You plant trees with root barriers around them. These are root barriers. You usually want to go put them at least 3.5, 4 foot deep. Or use herbicide pills, root barrier, biobarrier systems. The root systems hit them and stuns the roots, and they cannot go anywhere. Or put pots around the building. So you can put pots around the building and don't use trees. This is a Capital One out there on Westheimer. You had planter areas here. The building was moving around, highly expansive soils. The building was moving. So, and it was causing cracking of the building. If you go out there and look at it, they had the gravel in here. The tiles were coming off the building. The bed liners and gravel. Things were loose, bricks were coming off. So we told them to cover all the planter area and put pots there. The problem went away. Sewer leak, plumbing leak. On all the buildings, you got sewer leak and plumbing leak, causing settlement, water leaking underneath the foundation. You got to go in, put new plumbing in. Got to do tunneling. You can do plumbing tests to make sure there's a leak there. You do hydrostatic tests used for sewer line and sanitary lines. Fill the sewers with water and moisture for 30 minutes and see if there's any leak. You do video inspection. You use the video to check to see if there are leaks there. Cracks in the sanitary lines. Water supply pressure test. Pressurize the water lines for 5 psi above normal and measure and monitor it for 30 minutes. Here's a video inspection. You run it through the sanitary lines and look at there to see if there are any problems there. Roots are growing or there are cracks in it, leaking. Non-destructive investigation. Resistivity. If you want to know if there's a whole bunch of water underneath your building or not, if you get so wet and stuff like that, you can do resistivity. You put probes underneath your building and run current through it. Here's a medical building here. You do resistivity. Concrete's got high resistivity. Water's got low resistivity. You see pools of water underneath the building. This is the concrete floor slabs. This is where the water is underneath the floor slabs. Ground-penetrating radar. You can use GPR that penetrate. GPR uses an antenna that transmits electromagnetic energy similar to what cell phones do. A receiver also located within the antenna receives the reflected signal when it encounters the interface between soils of two different what we call dielectric properties. So you send a signal, it hits the object, it comes back. Question, what happened to the audio feed cutting in and out? I don't know what happened to audio feed. Does everybody have a problem?
It's
you may have just
on my end. No one else has complained. They can restart.
Okay. Okay. So this is the GPR. You run it out there, it sends them the signal out there on the floor slabs. And outside you can do it too. That's the GPR device in here. You got this thing out there on the screen. You can see where the pipes are underneath the floor slabs or underneath your paving. Here's a building out there. We want to know what's going on with the GPR on the floor slabs inside the building. Okay, here are basically the voids. These are where the voids were encountered underneath the floor slabs when we did GPR. Here's where all the wet areas are, the blue stuff. So we picked up the voids under the slab and the wet areas under the floor slabs. Okay. Geoforensic study of Voss Road. One of our roads out there in Houston had a bunch of voids underneath it. We used GPR underneath it. This, you can see the subsettlements in here happening on the road out there. Here's used to be a Buffalo Bayou. They went out and filled underneath. This is the road in here. This is the Buffalo Bayou. They filled this area here to build a road on top of the fill. The fill started settling. We used GPR and this is underneath the paving. We found all these voids underneath the pavement. Right there. They went out there and jackhammered this thing from what I understand, put a new pavement out there, asphalt pavement there. These were all the voids that were found underneath the pavements. Use GPR and found the voids. You can use GPR to find where the steel is in the walls or in the floor slabs. You run the GPR and it shows on the screen here, these are the steel, the spacing, the size. You can see if there's a pipe underneath. You can also use GPR to find out the compaction of the soil underneath the floor slab. The blue area has got a compaction of 85%. That's low, 85 pounds per cubic foot. That's pretty low, poorly compacted. The red area is properly compacted. So you can check the compaction underneath the floor slab with GPR. You can also see where area is good concrete. Concrete unit weight is 150 pounds per cubic foot. These areas about 150. The yellow is about 145. The blue is 130. So it's a kind of a low-grade concrete here. If you can check for basically leaks while using infrared, you can run infrared, basically measures the temperature gradient. This is a hot water leak out here in the kitchen. Infrared picks that up on a picture. You can see a leak in the carpet right there. Infrared picks it up. You can use infrared to pick up the hot water heater leaking. You can also do building surveys, stucco EFFs. You can say, supposedly, if the columns are missing, you can see if the insulations are missing. It's a leak around the basically light fixture. This is just good pictures of infrared. Talked about geologic faulting. This is the map of the fault. Somebody was asking about where you can find a fault map here. This is a typical fault map of Houston. It's not very accurate, but it shows kind of generally where some of the faults are. Here's a fault going through the structure, pavement, and cracking up the whole pavement system on aerial photo. Here's a delineation of the fault. Droughts, we went going through drought in Texas right now. In 2011, we had major drought out there. Texas was pretty much dry out there in 2011. You can see what happened to Lake Houston and Lake Travis. They both kind of dried up. Lake Travis, water was very little. Here's the rainfall in Houston, 2011. We had only 24 inches. It jumped up to about 56 inches in 2018. 2019 was 52 inches. 2020 was 44 inches. We had a deficit. We usually have about 52 inches of rain in Houston a year. 2021, we had 50 inches. Right now, we have 15.5 inches. We don't have deficit. We have enough rain this year so far in Houston. Here's a drought map of the U.S. in 2018. This is Texas in 2018. 2019 is a Texas drought. 2019. 2020, we had a major drought out here in west of the United States, Southwest. This is Texas in 2020. 2021, again, we had drought in California. Parts of Texas had drought. 2021. See the drought 2022, April 26. We have drought in Texas in the US. We have drought in Texas. So when you have a drought, the area of soil becomes really dry and gets to what we call, drops to what's called wilting point, near a suction value of 4.5. Its suction is referred to as a measure of energy, free energy in soil. Soil suction may be described as ability of an unsaturated soil to attract or retain water in terms of pressure, and is defined as a PF, which is a log 10 height of centimeters of water. Let's look at the foundation systems after a heavy rainfall. Typically, we get about, let's say, 50 inches of rain in Houston. In 2010, we had a drought. 11, we had a drought. If you build a slab of 2011, next couple of rain years, it rained and it was wet. What happens is, let's go back in here. Okay, here we go. It was dry and then it starts raining. And so what happens is, actually, this is a reverse. If this picture is diverse, you get this. This is what the picture you get. You get swelling at the edges. If it was dry and then you pour the slab and it rains, you get swelling at the edges. And if you get a situation where you build a slab, if the slab was installed after when it was wet and we had a big, and then it dried up, you got to get, I got this reverse. You got to basically get a shrinkage and center lift in here. So just depends. Again, if it was wet and you get a drought, you got a center lift condition. If you get a situation where it was dry and then we got rent, you get edge lift. Most of the houses or buildings are built. You need to look at aerial photos. Look at these ditches in here. They were backfilled and they were not compacted. They built all these houses in here. They had foundation problem because of the poor compaction of the fill. We had to go back and fix about 50 houses. They were not compacted properly. This is a ditch going through the Eagle Spring subdivision in Houston. Shows on aerial photos and shows on the quad sheet. They went that built on top of it, backfilled it. A lot of these houses along the channel here, they had foundation problems. You can see it on the quad sheet in here. Forensic engineer in court. Less than 10% of the cases in the US go to trial. Most of them settle after the lawyers make the money. For cases going to trial, the forensic engineer plays a major role. So when you do forensic investigation, you got to look things from different perspective. Take Mount Rushmore, this is the front. You got to check into it, it's the back. Pictures, send me pictures of your projects. If you got failures and stuff like that, you got a story to tell, we would appreciate it if you send me pictures. If you like this program, I'd like to have the program evaluation in here. Let's see if you can get that program evaluation. Let's see if you have it in here.
We send everyone a course evaluation at the end of this. Well, everyone that wants ICCCUs. I don't know if you do it differently for your engineers. Well,
this program supposedly does it, but I don't see it in here.
Okay.
Let's see if you have a, Vicky, if you hear me, tell me where the...
He probably has to do it from his side if he created that program evaluation. He has to shoot it out, not you.
Yeah, we'll send one out. I'll send one out and I can send you the responses.
Yeah, go ahead and send it out. And you got to do it right now because I'm going to shut it down in 5 minutes. So,
yeah, I don't know how to do that.
You know,
Vicky might be able to, but I mean, ours is after the fact.
Okay, so if you need to reach me, my email is de@geotecheng.com. Send me or email me your information to put you on a database. Send me an email with this email. My phone number is 713-699-4000. We have all these seminars coming up that are free. Well, some of them are free. Like we're going to have one coming up on May 11th on pools. That's going to be for Greater Houston Builders Association. I got 4 seminars coming up for ASCE. Anybody wants to member, these are free. So you're going to get your PDH hours. And if you have any questions, go ahead and ask the question.
What's your website called? What do they Google to get to your website?
My website is, let's see if I can get to it.
I'm going to use that when I'm doing field training and don't see expansion joints. I loved your line, David. Nature will put them in there if you don't. That's a good one.
That's true. Our website is geotecheng.com. Right here, geotecheng.com.
I had no idea trees were that big of a problem. On the energy, from the energy efficiency side, we typically think about the benefits of shading and lowering the solar heat gain through the fenestration and things of that nature. But, you know, foundation failure that's associated with them, who cares about your solar heat gain at that point?
Yeah, well, they affect foundation. Let's see, we have a question here. Can you go back to the webinar schedule slide? Okay.
Oh, those aren't webinars you're doing. Those are live trainings, aren't they? Or those webinars?
Some of them are webinars.
Okay.
Okay, like this one is going to be live training. It's going to be GHBA in Houston. ASCE on going to be 526 on slope stability. That's free webinar. On 6/9 is a free ASCE geotechnical for design of bridge structures. And 6/21 GHBA on design of residential foundations. And then on July 14th, we're going to have roadway design. It goes on and on. 7/28, design of water, wastewater facilities.
And all those are available on your website?
Some of them are, but yeah,
okay.
Some of them are available. So if somebody wants a link, send us. These slides cannot be given to anybody. Our slides are proprietary, but they can have our webinar link. Just see the whole thing, but not the slides. So any questions? Let's see, we got 3 questions here. Okay, very interesting, a lot of information. Trees are always the first item to investigate. Thank you very much. Thank you. Okay, let's see, quick Q&A. Can you go back to the webinar? I already done that. Can you get a link to your presentation? Yes. Send me an email. We'll send you a link, or
it'll be on our YouTube channel as well. If on YouTube, if you'll just search Spear SPEER Communications. We have 100 different webinars on our YouTube channel as well. And I'll send y'all a link too, David, if that's easier.
Okay, the other thing is, here's another question. What is acceptable tilt on a home? Is 1%. I've been seeing a lot of tilt foundation in my area in San Antonio. Another question, is wall crack always connected or caused by foundation problem? No, sometimes because of the humidity and other things. Jointing and all that stuff. Is there a state of law requiring soil report for foundations? Texas Board of Professional Engineers says that you should have a soil report when you do foundations for building. If you send me an email, I'll send you Texas Board of Professional Engineers' opinion on that. Awesome. Building some pools here lately, curious. Well, come to the pool seminar. 99% of the pools in Texas are done without a soil report in the pool, what we call pool reports. Next question. Thank you.
Mine. When I was inspector for the city of Temple, we didn't require a soil report on residential slab. We allowed we called it a type 2 foundation, you know,
yeah.
And
well, type 2 is not very strong. Webinar on pool. We got a webinar on pool coming up next month for GHBA. Thank you. Always useful information. Somebody's giving their email. Email me your information.
Yeah, you've said that 3 times already.
So, I mean, thank you. Always useful. Let's see what else. Michael, okay, done. Okay, I think we're done in here. I appreciate your time. Again, if you have any questions, send me your email. You got my email address. Thank you very much. All have a great day. Thank you.
Thanks. Appreciate it, everybody.
Bye-bye.
Fantastic. Great job, David. Thank you.
Thanks.